So let's go back again and look at a little more of conservation of mechanical energy with another example problem here. Sliding down a hill, a frictionless hill. So they've already given you the setup here that there's no friction, no non-conservative forces. So a sled and its rider together weigh 800 newtons. So that's the two of them together. They move down a frictionless hill through a vertical distance of 10 meters. Okay, same height as the last time. Use conservation of mechanical energy to find the speed of the sled rider system at the bottom of the hill, assuming the rider pushes off with an initial speed of 5 meters per second. So you've kind of seen this one in the last one. So if we look at the givens, we've got 800 newtons of force. We've got an initial height of 10 meters. We've got a final height of 0 meters, so top of the hill, bottom of the hill, and we've got an initial velocity of 5 meters. Okay, so we're going to go through and find the speed of the sled rider system at the bottom of the hill. So we start off the same way. We're going to start off with our grassroots relationship here, the 1/2 mv squared, blah, blah, blah. And we are going to simplify it. Since the mass is, again, constant, we're going to remove the mass from each relationship, which we can do. Mathematically, that is something we can do. So when we run through and put all of our values in, 1/2, 5 meters per second squared, 9.8 meters per second squared, 10 meters, 1/2 velocity final squared. Okay, that's the term we're going to solve for because we don't know the final velocity. And we know that we have at the bottom of the hill, mgy is going to be 0. So it starts to simplify very quickly for us. So we've got 12.5 meters squared per second squared, 98 meters squared per second squared. That's nice. We've got units that match, so we can add the two together, is equal to 1/2 final velocity squared. So once we do that, then we can move the 2 out of the denominator on this side, move it to the numerator on this side, and once we combine our terms, multiply them times 2, we get 121 meters squared per second squared. Take the square root of both sides, and we get 14.9 meters per second. Pretty close to the value that we got on the last one. Remember, we got 14.1 and 14.0. So you see how we can move through these relationships and do a little bit of substitutions and cancellations to simplify the math. So now what they want us to do, if the sled and rider start at the bottom of the incline and are given an initial uphill push of 5 meters per second, how high will they rise vertically, and what will be their speed when they return to the bottom of the hill? Okay, so a lot of this stuff is the same, except for the fact that at the bottom, we have an initial velocity of 5 meters per second. So again, we start with our simplified relationship, determine where we can put our zeros in. The initial height, the initial velocity is 5. The final velocity will be 0. That's when it'll come to rest. And so, again, we start putting our values in. We start looking for where we can combine terms. Look at the units. Once the units start playing out, you know that we've got values that we can combine. So 12.5 meters per second squared, 9.8 meters per second, okay, ends up with a y final of 276 meters, okay? So now we go back to the relationship again, give it, again, our initial velocity of 5 meters per second, y final equal to 0, and solve for the velocity again on this side, and we end up with 25 meters per second squared. We take the square root of that, we get 5 meters per second. So that'll be the speed of the sled when it returns to the bottom of the hill. So we're taking different aspects and different ways of looking at our problems here so that we can look at manipulating these relationships and figuring out when we can do cancellations, when we can do combinations. So this is a classic problem, a classic explanation or example in conservation of mechanical energy, the spring. And what we're going to see is you can look at springs in a lot of different ways, a lot of different applications. We look at a spring being fully extended. And when it's fully extended, neither compressed nor stretched, it's in equilibrium. Typically when it's completely stretched out like this, we talk about it being in tension or compression. Okay, as we start to move the box back and compressing the spring, you can see we've moved it through some distance. So this is starting to give us some hints that we might have some relationships here that follow along with work. Okay, so we move it some distance x, and the spring starts to compress. So Hooke's law says then when a spring is stretched or compressed from its equilibrium length, the spring exerts a restoring force. Okay, so this will be an F with an R as a subscript, the restoring force. That is proportional to the displacement of the spring from equilibrium. So we see we started in equilibrium, we start compressing the spring starts trying to fight back with its restoring force. So you can see here we can use our relationships for potential and kinetic energy to try to solve some of these relationships. You'll notice now our relationship for potential energy in a spring, the little s, is 1/2 k x squared, where k is our spring constant. The spring constant is based upon the metallurgy of the spring itself, the spring tension, if you will, or the tensile strength of the spring that causes it to spring back. So the force is equal to kx. K is the spring constant. F sub s, the force of the spring, is equal to minus kx for the spring in compression. Okay, this equation then for F sub s describes the force exerted by a stretched or compressed spring. So you can see at some point, if we let it go and the spring goes back to its equilibrium point, we end up with the potential energy of the spring 0, but now we have a kinetic energy back to our 1/2 mv squared. So in looking at the elastic potential energy in a system here, in a spring, to determine the work required to compress a spring from its equilibrium position to some arbitrary position x, the following applies. So the relationship is telling us that some average value, the force initial, the force of x, okay, the distance divided by 2, and setting the initial point to 0, you can see that it simplifies very quickly, f sub x divided by 2, and we end up with that relationship, 1/2 kx, where f sub x now is kx. So therefore, if we look at work and define it, if you will, the average force times the distance is equal to 1/2 kx squared. Okay, so the definition now that we have when dealing with a spring potential energy is 1/2 kx squared. So if we take what we've already been given, our kinetic energy initial, our potential energy initial, potential energy to gravity, potential energy to a spring if we've got a spring. So now you can see we've kind of got a cafeteria style here, a buffet. You have to decide which of these you're going to keep and which of these you're going to use as you're trying to solve this type of problem. So when the block is released, the spring snaps back to its original length. It wants to go to complete uncompressed condition. And the stored elastic potential energy is converted to kinetic energy of the block. So you can see here by our relationships, the potential energy at the end is 0. The kinetic energy, because the block is moving, is our 1/2 mv squared. So we can look at a problem here before we move on to the next video. A 1/2 kilogram block rests on a horizontal frictionless surface. Okay, they made it easiest, no friction. The block is pressed against a light spring. Okay, remember what I told you about light springs and light strings? That means that the mass of the spring does not come into play. Having a spring constant, though, of K equal to 80 newtons per meter. Write that down. K is equal to a value, newtons per meter. Okay, so that may be a conversion you're going to need later. The spring is compressed to a distance of 2 centimeters and released. Consider the system to be the spring and the block. Find the speed of the block when the block is at x equal to 0. So from the problem, we're able to glean the mass of the block, the spring constant, and the distance. Okay, so now we start with our buffet here. Kinetic energy, potential energy, initial, final. So let's look at the problem and determine which of these terms immediately go to 0 that we can get rid of. Well, the potential energy of gravity is 0 on this because there's no y-axis. There's no up and down in this problem. So throw that one away, get rid of it. Kinetic energy initial is equal to 0, okay? Because when we start the problem, there's no kinetic energy associated. It's all potential. So we're left with potential energy of the spring initial is equal to the kinetic energy final. So knowing that potential energy of the spring initial is equivalent to 1/2 kx squared, and the kinetic energy final is 1/2 mv final squared, we can take those values and put them into our grassroots equations here. Okay, so we set one side equal to the other. Now we can start dropping the numbers in. So 80 newtons per meter, 2 times 10 to the minus 2 meters. We did this because we've got meters. We're going to take our 2 centimeters and we convert it to meters. It makes it easier. Do that up ahead, at the beginning of the problem. And then 1/2 0.5 kilograms, that's the mass of the block, times the velocity final squared. We don't know yet. That's what we're solving for. So as we move our terms around, simplify the problem, we end up with 1.6 times 10 to the minus 2. I don't have my units on here, shame on me, divided by 0.2 or 1/4. Okay, we're going to divide it by 4 in essence here. So the final velocity in this case, once we take the square root of both sides, is 0.25 meters per second. Okay, so we're going to stop there. When we come back, we're going to look at non-conservative forces and the work kinetic energy theorem.